Dark matter is one of the primary components of the universe. And in fact, we think that there's more dark matter in the universe than there is normal matter. And I'll talk to you about what this dark matter is and why it's so weird and why scientists are so excited about the possibility of potentially detecting it during this lecture. So if you recall, the story that I've told you so far goes something like this. In the 1800s, leading into the late 1800s and early 1900s, astronomers knew that there were some things up in the sky that were puzzling, and these things were nebulae. They're called nebulae. And most of the time, astronomers would see them away from the plane of the disk of the Milky Way. So remember, you look up in the sky, and especially on a really dark night, you'll see a band of stars, or a milky band in the sky, and that's the Milky Way. And what we're seeing is a projection of ourselves living in this giant disk of stars. Okay, so we're in the outskirts of this disk, and we're just looking at it. We're embedded within it, and that looks like a plane that cuts across the sky, kind of like looking at a dinner plate on edge. Okay? And astronomers in the late 1800s, early 1900s were really interested in this dinner plate that we lived in, this disk of stars. And they wanted to study stars in this dinner plate, and they wanted to study planets in our solar system, and they were fascinated by this stuff. And they spent most of their time cataloging and looking at stars in this plane. Okay? Now, if you look off the plane, a lot of times, they would see these nebulae-looking things, and some of them were spiral nebulae that look like this. And they tend to live away from the plane, or at least they were easier to see away from the plane. And most astronomers were spending all their time on the stuff in the plane, because they figured, well, I don't know what this little fluffy stuff is out here, but all the main action's going on in the plane. I want to study the stars and stuff going on. But not everybody, and so there were a few people like, for example, James Keeler, who was the director of Lick Observatory up in Northern California, and he was interested in taking pictures of these things. And this picture right here was taken of one of these spiral nebulae in 1899. Okay, so this looks like a modern picture of a galaxy. Looks a lot like the pictures that even Hubble will take of galaxies now, except, of course, it's in black and white. And the other thing that he noticed, although it's hard to see in this picture, you can see it on the PDF. Up in the left corner here, there's another one. So you see this one that's right in the middle. There's another one up there. It's kind of like this. And what he found is that as he exposed longer and longer with bigger and bigger telescopes, suddenly he'd see more of these things popping out if you look deeper. You'd see more of them. It's almost like there were all these nebulae out there that they didn't know what they were. Now, eventually, the story I told you is that in the 1920s, Edwin Hubble, this guy, used what was then the largest telescope in the world to resolve individual stars, first in the Andromeda Nebula, the Andromeda Spiral Nebula, and show, therefore, that it was actually a galaxy in its own right. And this began to add evidence to the idea that these things that were classified as spiral nebulae were actually other galaxies. And the idea began to emerge that the Milky Way itself was actually a spiral galaxy that looked like this, and we were just living out here. And so when we look at it, we see it like an edge-on plate. But there are other galaxies living out here that sometimes we see, and we see them looking like this or like that. And today we can make pictures like this. So this is just a map of all the galaxies within about 300 million light years of us. And every dot here is a galaxy. There's not enough information and there's not enough pixel resolution here to show you, but every single one of these dots is as interesting as this thing here. And each one of them contains 10 billion to 100 billion stars. So this was a big discovery that Hubble made, that the universe is actually filled with galaxies, and that's the way to think of the universe. The universe is a universe of galaxies. The universe is not a universe of stars. Okay, so really, each galaxy is an island of stars. There are many, many islands throughout the universe. But given this new telescope that Hubble had access to, he was not done there. So he was continuing to explore and say, okay, well, what's going on with these galaxies? Is there anything else we can measure about them that shows anything else interesting? So in the late 1920s, around 1929, he published a study of 25 galaxies. So he was able to resolve stars in 25 galaxies, all of them fairly nearby by our standards. And he was able to measure the distances to these galaxies using this method of Cepheid variable stars that we've talked about. Okay? And he compared the distances to those galaxies with the speeds with which they were moving. And he found that the farther the galaxies were away, the faster they tended to be moving away from us. So it's as if they were all moving away from us, and the farther they were away, the faster they're moving. So this hinted at this idea that the universe is expanding. And then in 1931, he got more data. And specifically what he did is he went after some galaxies that were even farther away. And he wanted to see, well, if this is true, then the farther away the galaxies are, the faster they should be receding from me. And I ought to be able to measure that. So he looked for galaxies that were really far away, and he measured how fast they were receding. And he found it worked. It kept going. They were in fact, moving away really fast. So this next slide is a paper that he published 2 years later with Humason in 1931. And this plots the recession velocity of the galaxy versus the distance to the galaxies. And all the data from his 1929 paper was in this little corner here. So he added these new points to his plot, going way out. And what he found is, as he kept going out, the universe kept expanding. And things were moving away faster and faster and faster. So really with this kind of solidified the case that the universe was indeed expanding, or at least the galaxies were moving away from us in apparent recession. And this, of course, is a big deal. The law that describes this relationship between velocity and distance is called Hubble's law. It says that the velocity of a distant galaxy is equal to its distance times a constant h0, where h0 is called Hubble constant. And the variables in this equation are given by this. Now here, I'm going to show you another Hubble diagram that's from a later data set. And I showed you this last time. We've already talked about this. Let's say you go off in some direction. Let's say here. And you look at galaxies that, say, run along this direction. And you just plot the velocity with which they're moving from us versus their distance and see what you see. So you see something like this, where these are the velocities, these are the distances, and here are all the dots. So what's interesting about this figure? I showed it to you last time. I wonder if people remember. Yeah. Chunk in the middle. There's this stuff. Okay? So all this stuff here, you can see, because this line is distance, all these dots are at about the same distance. But they have lots of different velocities. Do you remember what's going on there?
It's a cluster of galaxies and they're
Right. Great. It's a cluster of galaxies. So there's a group of galaxies that are all really close to each other in distance to us, but they have lots of different velocities. So what we think is going on is they're all going around each other. So the whole galaxy cluster. Imagine it just a big ball of galaxies is moving away from us like this. But in the process of moving away from us, the galaxies are going around each other like this. So some of them we catch going towards us a little bit in the recession. And those are the ones that live down here. So they have they're a slightly slower recession velocity. And the ones that lift up at the top are the ones that are moving around each other in a direction that's in the same direction that the whole cluster is moving. So it's as if the velocity is boosted a little bit. And you can see that in this picture. So if you can measure you say, okay, well, let's assume the middle of the cluster is moving with the expansion of the universe. The speed with which they're moving around each other gives you some indication of, if you were in the cluster itself, so you didn't know it was moving, you would just see galaxies whizzing around. Okay, so what's happening then is these clusters are all the galaxies in the clusters are whizzing around each other, and then the bulk themselves are moving out together. Does that make sense? Are there questions about that? Okay. So, all right. So for example, let's pick on this cluster right here. This cluster is called the Coma cluster. It's pretty nearby and it's pretty big. This is what it looks like. So these are two really big galaxies, but there's a bunch of little galaxies in it too. They're all going around. Now, there are other astronomers who are interested not just in measuring how the universe is changing on a whole, but they're interested in understanding these clusters as well. And it turns out that if you measure the speed with which things are going around each other, it's a reasonable way to measure the mass of something. Okay? So, what do I mean by that? So, for example, the moon is going around the Earth with some speed. And the speed with which it's going around the Earth depends on the mass of the Earth. If you change the mass of the Earth, let's say you made the mass of the Earth bigger, then the moon would move towards the Earth a little bit. And similarly, the speed with which the Earth is going around the Sun is determined by the mass of the Sun. If the mass of the Sun was different, the speed with which the Earth was moving would have to be different to be at the same distance. Okay? And so if you can measure the speeds with which things are orbiting around each other, it's a good way to determine masses. And that's all determined by, for example, Newton's laws of gravity. So what I mean by this is, if you've got a cluster of galaxies that are all whizzing around each other, and those velocities are small, then you think this whole thing is a small mass, doesn't have that much mass. If all the velocities are big, you suspect this thing has a big mass. Because the bigger the mass, the faster things have to be going around each other to be in equilibrium. Is there a question about that? So it's one way to determine the mass of something. And there was this guy named Fritz Zwicky. There he is, right there. Who wanted to go out and he wanted to measure the speed with which these galaxies are going around each other in the Coma cluster. So he did this around 1930. And when he did this, he found something that was pretty surprising. So what he found is that these galaxies were going around each other way too fast to be accounted for by all the mass that you can add up. So if you add up all the masses of all the stars in all these galaxies and from that figure out how fast they ought to be going around each other. That speed is much more small than the speed that he measured. To put it another way, if these galaxies are going that fast, there's not enough gravity there that you can see to slow them down. So they're either going to go right through each other. So remember, you're looking at them along the line of sight. And some of them are going this way and some of them are going that way, according to you. So if there's not enough mass there, then you happen to just be catching them moving through each other. And if you waited a little bit of time, they would just fly through each other and there would be nothing left. They would totally evaporate because they're moving that fast. It's almost like the idea of escape velocity. So if you launch a rocket off the Earth going really, really fast compared to the escape velocity of the Earth, it'll be gone pretty soon. But if you launch a rocket very slowly or just throw a ball up very slowly compared to how much mass the Earth has, it'll turn back around and maybe orbit around the Earth or just come back down and land on it. But if these galaxies are moving so fast that unless there's some additional mass there, the galaxies should just go away pretty soon. They should evaporate pretty soon and just pass by each other and keep moving. There's not enough mass to bring them back. Does that make sense? Well, I mean evaporated in the sense that
They wouldn't be orbiting.
it wouldn't be orbiting each other anymore. They would just fly off to far away. Kind of like, Jupiter's going around the sun, but if you just got rid of the sun all of a sudden, Jupiter would just fly off. So the idea then was that there was some missing mass. And this missing mass we refer to now as dark matter. There's some missing mass there that we can't see. And the amount of missing mass estimated by Zwicky was about a factor of 10. So he said there's got to be something like a factor of 10 more mass there than we can see. So there's some other stuff there that's holding all these galaxies together to orbit around each other. Now, most people pretty much ignored it. Okay, Zwicky was not. No, Zwicky is a very interesting character. So you see, he's going like this. Let's see, he's doing this, right? And this is something that Zwicky did a lot. So what he was doing is he calls people spherical bastards. Spherical bastard, he calls people. You know why he calls people a spherical bastard? The sphere is a thing that looks the same no matter how you look at it. So spherical bastard is someone who's a bastard no matter how you look at them. So that gives you a little bit of insight into Fritz Zwicky's personality. Some people didn't like him. Some people thought he was crazy for suggesting that there's all this mass out there that you can't see. Interestingly, though, there's another astronomer named Smith who, not too long after this, looked at galaxies in the Virgo cluster, which is another nearby cluster of galaxies. And he basically found the same thing. He also found that the galaxies in the Virgo cluster were going around each other much faster and could be explained by their own internal gravity. So, I think I said, so in the previous slide, I should correct myself. I think I said he claimed you needed 10 times as much dark matter as the mass you could see. What he was saying is more like 100 times as much dark matter as the mass you could see. That was my mistake. So, what he's finding is that the velocities of galaxies in the Comet cluster were something like 1,000 kilometers per second going around each other, which is a really fast, really big mass. And this is the reason then for the idea that maybe there's dark matter. Let me flash forward to modern times when we can study the Coma cluster with different types of instruments. And we now have pretty good evidence that there is such dark matter around the Coma cluster. And one of the reasons why we know this is that we can study the Coma cluster in X-rays. So let me explain to you what's going on here. This is an image of that same cluster in visible light. So we're seeing galaxies here. And this is an image in X-ray. So this is what this thing looks like if you just look at it in X-ray. This is huge on the sky. So this is a very, very big distribution of stuff that's glowing in the X-ray. And the stuff that's glowing in the X-ray is gas. It's hot gas. It's not dark matter, okay? But yet it's hot gas. So we think that there's gas, hot gas, that's filling all the voids, all the regions in between these galaxies. And the gas is so hot that it's difficult to understand how it could be contained like this if there weren't a whole lot of mass to hold it there. Okay? Otherwise, this gas, just like the galaxies that are moving fast, would float away. But put it another way, the pressure of that gas is so high, unless there's a lot of mass to hold it together, it would just expand and go away. See what I mean? And in fact, the mass you estimate from this X-ray measurement, using its pressure, is very, very, very similar to the mass you estimate from using the velocities of the galaxies themselves. So there's two independent checks using completely different methods that suggest that there is a lot more mass there than we can see. Now it turns out that there is a lot of mass in this gas itself, but not enough to account for the more than 100 times additional mass you need. We're still way off here. There questions about that? But let me move forward then. So in the 1930s, people didn't know about this. There weren't X-ray telescopes like this, and most people just thought Zwicky was just kind of crazy, and they sort of went on with their lives. But flash forward to sort of the 1960s. In the 1960s, astronomers began to look at individual galaxies and study their kinematics as well. So instruments became good enough. The instruments that astronomers were using, they were sort of sticking them onto the ends of telescopes. They became sophisticated enough such that you could do things instead of just taking a galaxy and measuring how fast it was moving towards us or away from us. You could measure how fast one side of the galaxy was moving and the other side of the galaxy was moving. So, for example, if you ever had a disk, you could show that it tended to be that they spun around themselves like this. In one side of the disk, you would see it, you'd be looking at it, you could see that one side of the disk would be moving towards you and the other side was moving away. That's called a rotation curve. So you can map out how fast the galaxy was spinning from the center of the object out to the edge. And why do we care about this? So one of the reasons why we care about this is you can use this, again, to measure the masses of things. In much the same way that, note this is a plot of the solar system. This is the speed with which planets go around the sun. And this is the distance to the sun. The Earth goes around the sun at about 30 kilometers a second. But as you go to planets that are farther and farther away, they go slower and slower. Saturn's only going around the sun at 10 kilometers per second. And way out here, Neptune is going around the sun at something like 8 kilometers per second. So as you get farther and farther away from the sun, the speeds that are moving get slower and slower. And that's because you're getting away from the mass. The farther you are away from the mass, the slower things should go around, because the force of gravity is weaker. Does that make sense? Okay. So in principle, if we wanted to, this would be one way to measure the mass of the sun. You could measure how fast planets are going around the sun, and you can use this to figure out the mass of the sun. If we wanted to measure masses of other stars, this would be a way to do it. If you find things orbiting around each other, it's a way to measure masses. So the woman pictured here is named Vera Rubin. Vera Rubin, along with a few other astronomers, like I said, in the 1960s into the 70s, spent a lot of time measuring the rotation curves of galaxies, trying to measure how fast galaxies are going around themselves. She became a master of the new, what was called CCD technology, the same CCDs that you have in your digital cameras now. Those are just being used by astronomers in this time. And she used these techniques to really open a new window into determining how fast the masses of galaxies, basically. I should add in passing that Vera Rubin, who's still alive, by the way, her son is Carl Rubin, and he holds a mathematics chair in UCI, so he's in our mathematics department. You'll see him sometime at events and things. So brains apparently run in the family with this family. And so here's one thing that Vera Rubin was trying to do. So here's a galaxy you're looking at, right? And what you want to do is you want to measure how fast the stars are going around from the center. You look at this galaxy for a second, you see there's a lot more light in the center than in the outer parts. So you expect a lot more mass in the center than the outer parts. From that expectation, you think that the speed with which stars ought to go around ought to be pretty high in the middle, and then it ought to fall off as you go to farther and farther distances from the galaxy. But what we find is not that. What we find instead is that the speed with which stars go around tend to be pretty flat in the outer parts of galaxies. They're not declining like they would if the mass was really falling off. So what this suggests is that there's a lot more mass out there that we just can't see. Okay? And so this is an additional piece of evidence that there are big, what we call halos of dark matter, big extended distributions of missing mass out there. that are acting on these stars to make them go around fast. And this is the same kind of thing that Zwicky was talking about with the galaxies going around each other in the clusters. Okay. Other questions about this? Yeah.
So the dark matter makes the rotation stay.
Pretty much constant, yeah. I mean, it's not exactly constant, but yeah, makes it stay pretty much constant. Other questions about that? So, and this is seen not just in one galaxy, but in every single galaxy we look at. So every single galaxy that we study like this, we see evidence for this missing mass. The same is true in our own galaxy, the Milky Way. We see evidence of this missing mass when we look at how fast things are moving around in the outer parts. What's more, as time goes on, we're finding more and more ways to test this idea. So it's as if, I mean, for example, let me put some numbers to this. If you look at this, the implied amount of mass that we need to add to the galaxy in order to make this happen, we're talking about, again, more than a factor of 10, something like 10 to 20 in a galaxy like the Milky Way. 10 to 20 times as much stuff out there making the stars go around fast than we can actually see. So it's a lot. It's not just like the same amount of mass in stars and dark matter. It's way more mass in dark matter than stars. So obviously this now starts to get people's attention, because now we have two sort of separate pieces of evidence that there's something funny going on with the dynamics of galaxies and clusters and the speed with which galaxies spin around. There's another technique that people use to study masses in the universe, and this is called gravitational lensing. So let me talk a little bit about what this is. So according to Einstein's general relativity, let's try it again. According to Einstein's general relativity, when you have a mass, okay, when you have matter, it warps space. So in close proximity to the mass, space gets bent. And what Einstein showed was that in principle, if you have a massive thing and you have a distant light source, that light source, while the light would normally go straight by the object, in the presence of this curved space, it can get bent a little bit. So if you're here looking at me and there's something heavy sitting here, light from distant sources will come by and then get warped and bent. Much the same way that if you had a lens, if light went through the lens, it can get warped and spin around and change shape, change the way it propagates. Okay. Now, interestingly, back in the day, back when they were first working on general relativity, the expectation was that this is a very rare phenomenon. It happens sometimes, but there's not enough mass in the universe to make this happen very often. So in very, very special circumstances, like, for example, if there's a star that's very closely aligned with the sun, you might be able to see some effect. You would have to observe it during an eclipse. And this is one of the observations that people use to prove general theory of relativity, or at least help solidify it. But now what we find is that this gravitational lensing happens a lot. And it happens a lot, especially with distant galaxies and galaxy clusters. And the reason why it happens so much more than people in the past thought it was going to is because we have all this additional mass out there that no one was counting on. There's all this dark matter out there that initially we weren't counting on. So if you look at this system right here, you'll see this is actually a picture of a galaxy cluster. These yellow things here are galaxies living in this cluster, all living together. But you see this thing right here, this orangish arc right here. What that is that's light actually from a background galaxy that's being bent. So the light is going through the cluster and it's being bent in such a way that it makes the shape of an arc. If you've ever held a wine glass and looked at a light through it, you'll sometimes see arcs, sort of like that. So the idea is, for example, if you have a light, so here's a heavy thing, say a galaxy, and here's a light source, say a galaxy behind it. If that thing's lined up right behind it, right behind the line, then light will get bent out from it and then bent right back. And that creates the image of a ring. That's called an Einstein ring. And if those Einstein rings aren't perfectly complete, you'll see these arcs. By measuring the nature of these arcs and how frequent they are, you can determine the mass of this thing and how much mass needs to be there to make this happen. And we see this all the time. So these are real images here of galaxies that are doing gravitational lensing to objects behind them. So here's an arc. This is a galaxy doing the lensing. These two dots, you see this thing right here, this is another galaxy. These two dots right here are a distant light source, and it's the same thing. So this dot is some galaxy, and this is the same galaxy. And we can tell because if you look at the spectrum of light from this thing and the spectrum of light from this thing, they're identical. So we can tell there's the same galaxy. But the light is being spread out and bent back. Much the same, you can imagine this happening. You have an experience with this kind of thing happening with mirrors, right? You know light can get bounced around with mirrors. It also can happen with lenses. You can create two images of the same thing. That's what's happened here. Except now the thing that's acting like a lens is actually the gravity of the galaxy itself. With mathematical models, you can determine exactly how much mass this thing has, and when you do that, you find that it has to have a lot more mass than you see in the stars. So this is just one more picture of this kind of thing. Everywhere I've drawn an arrow here, you'll see a little arc. So there's an arc, there's an arc. It's not showing up super well just because of the projector, but there's another arc. There's a few more. So what I'm trying to get out here is there are a number of methods that astronomers are using to explore what the universe is made of. And what seems to be the case is that there's a lot of additional mass out there that we can't account for. And this missing mass is called dark matter. So just to enumerate some of the things that I've just said, there's lots of different pieces of evidence for dark matter. And actually, this is a limited list. There are actually more than this. But I think this is probably good enough. So the first thing that I talked about is galaxies and clusters zoom around each other really fast. And the speeds with which they go around each other is much higher than you can explain with only the light from the stars, which suggests that there's additional mass. Galaxy rotation curves, the speed with which the stars spin around galaxies, are too flat, meaning that the speeds with which stars are going around does not decline at the edges of galaxies, but if anything, it speeds up or stays the same. This is not expected if the mass in the galaxy follows along with the stars. The other thing that I mentioned is that we can also study the hot gas in galaxy clusters, because we can see it's emitting in the X-ray. So if we study galaxies using X-ray telescopes and study the hot gas in galaxy clusters, we can determine that this gas has a high temperature and a lot of pressure. And if there wasn't a lot of gravitational force holding it in, then it would fly away. And so there's an additional piece of evidence that that mass is there. And finally, there's this other technique called gravitational lensing, which uses the fact that gravity bends light, and in bending light, it creates this effect of a lens. And that's another way to measure masses of astronomical objects. Now, just a hint, when you're making a test, you're always looking for lists and enumerations. It's the easiest thing to try to test on. So, you should know these 4 things. This is like the easiest thing to make a test question out of. Which of the following are evidence for dark matter? All of the above. Okay. So, questions? So what is this dark matter? What do we think it is today? Well, first of all, it's called dark matter, and the only reason it's called dark matter is that it doesn't shine. Okay? It's dark. So that's pretty simple. But there's a little bit more to it than that. Okay? There's a little bit more to it than it doesn't shine. What it means in more detail is that it doesn't really interact with light in any significant way. And when I say light, remember, I'm talking about electromagnetic radiation, which itself is coupled, which is related fundamentally to the electromagnetic force. Now, I'll talk more about that, but that's a very fundamental thing, and that's very, very different than what we experience in everyday lives with normal matter, what we call normal matter. So because of this, it interacts very, very weakly with normal matter. So it doesn't interact very strongly with protons, neutrons, electrons. Well, protons and electrons at least, and the molecules. And most astronomers, most professional physicists, cosmologists, and astronomers think that the dark matter is made up of some as of yet undiscovered subatomic particle. So a subatomic particle that we don't know anything about. So just to clarify, everything in the periodic table is made of neutrons, protons, and electrons. So every form of matter studied in the chemistry department is out the door. That's not what dark matter is. It's something entirely different. Something that's completely undiscovered so far. Yeah?
Does it consist of atoms? Or?
We don't think so. So it doesn't consist of atoms in the way that we think of atoms, like these things. It doesn't have neutrons and protons or anything like that. And current measurements suggest that there's about 6 times as much dark matter as normal matter in the universe. So, to put it another way, we have no idea what 80% of the universe is, or more than that. Okay. So let me explain to you exactly why this is weird. So the thing that's very weird is this thing that I said it doesn't really interact strongly with light. So imagine you had a ball of normal matter, and the ball is traveling towards the wall. Hits the wall, it bounces off. But if you have a ball of dark matter that's traveling towards the wall, it'll go right through the wall. Well, why is this? So why does the ball bounce off the wall? Sorry?
There's matter there.
Okay, what does that mean? So, what do you mean there's matter there? You mean there's atoms there?
Force of the atoms.
Okay, the force of the atoms? Okay, that's good. What do we mean by force of the atoms? What kind of forces? Yeah, it's good.
Some kind of electrostatic.
Yeah, it's electromagnetic force. It's good. This is good. So there's electrons in the outer parts of the atoms in the wall, and there's electrons in the outer parts of the atoms in the ball. And when they hit each other, those electrons repel each other because they're both negatively charged. Okay, that's the same thing that prevents me from falling through the floor. The nuclei of my atoms are not touching the nuclei of the floor atoms or molecules. Right? There's no nuclei touching each other. Remember that if an atom were the size of a football field, the nucleus would be like a little marble in the middle. The electrons are the things that shape the atoms. So all interactions that happen between atoms are really shaped by the electrons bouncing into each other. So now if I come up with this type of matter, this dark matter, that doesn't interact electromagnetically, that doesn't have any charge, it has no electrons in it. If it runs up to the wall, it just goes right through. because there's nothing for it to interact with. Now we think this is true because if it wasn't true, we would have detected it already. We would see it. We've been studying these galaxies for a very long time, studying these galaxies clusters for a very long time. Whatever mass is causing all of this kinematic stuff, all of this dynamical stuff that we see, whatever is doing it cannot be interacting with light or electromagnetic radiation in any significant way, or else we would have seen it already. And this is one of the reasons why we think it's some undiscovered type of particles. We don't really know any type of particles like this. Yeah?
Why, the picture you showed a minute ago, then the X-rays of like the gas that was like holding it together, then why was it holding it together instead of just
Good.
pass through?
Great. So you're saying, well, there's all this X-ray gas out there that's hot, that's emitting X-rays. How is the dark matter holding it together if you can't touch it? What I mean by holding it together is it's gravity that's holding it together. So it's almost the same as, imagine something really massive at the center of it. This is not really how it works, but if you had something really massive at the center of the cluster, it's got such a strong gravitational pull that it can keep all that mass, can keep all that gas attracted to it. There's a lot of mass there that's attracting stuff by gravity, and it's the gravity alone that's keeping that hot gas orbiting around it, all because of gravity. It's not touching it and pushing it or any way. It's not applying a pressure. It's only tugging on it by gravity. In the same way that the sun keeps Saturn there. It's just tugging on it with gravity. Every single little gas particle that I was showing you in that picture is being tugged on by the gravity of the dark matter of the cluster. Are there any other questions? Yeah.
So the gravity of the dark matter is everywhere then, and then it has
Well, we think that, so the dark matter we think is clustered, is basically made up of balls. Not exactly, but you can think of it around every galaxy, there's a distribution of dark matter that extends out from it. And around the galaxy cluster, there's a big distribution of dark matter that surrounds that galaxy cluster. So what we think is going on is, imagine the dark matter in the universe is like a series of mountain peaks. All the galaxies we see are like snow dusting the tops of the mountain peaks. So what we can't see, imagine you can only see the snow. So you would see the snow just kind of peeking up on the horizon. And you just can't see the mountains that are underlying it all. So we think that there are these vast mountains of dark matter, and down at their very centers are these lit up balls of stars that are the galaxies. So let me show you another example of astronomers trying to study this stuff, because the dark matter thing is very weird and very mysterious, but it's also quite exciting, because what it suggests that the universe that exists is much richer than you would guess from just knowing the periodic table. You might think that the whole universe is well understood, because we can put it in a table, right? We give names to everything, we know all the interactions between stuff. But everything in this table is just a tiny, tiny fraction, at least we think. Everything in this table is just a tiny, tiny fraction of what makes up the universe. This is just a sliver of the universe. And it's as if there's this whole unseen universe that's been discovered in the last 70, 80 years that's lurking out there that we're trying to figure out. So here's a pair of galaxy clusters that has actually provided some interesting insight into this question of the dark matter. At least it's another way of looking at it. And it's a rare pair of galaxies. This is actually called a rare pair of clusters. It's actually called the Bullet cluster. I don't know why. But here's a cluster of galaxies and another cluster of galaxies. And what we think has happened is that these galaxies have gone through these galaxy clusters have gone through each other. So one was moving one way and one was moving the other way, and they've just passed through each other. And why is that? Okay, so this is how we think they're moving like this. They're going through each other. Now, these galaxies have not only been studied in optical light. So this is visual light. This is what you see if you point a space telescope at it, like Hubble. You see these galaxies all over the place. You see two galaxy clusters there. But then if you study it in X-ray, and you also look at the gravitational lensing induced by this galaxy, you can make other types of maps. So this blue, what's shown in blue, is the inferred gravity from this thing. So this all comes from gravitational lensing. So this says most of the mass is right here in this guy, and most of the mass is right here in this guy. Now this red stuff, that's X-ray. That's an X-ray image of this thing. So this is all hot gas. Now notice what you see here. Let me take that off. This hot gas piece, notice how there's a blob here and there's a blob here, and they stand on the other side of this blue. So what's happened is you've had these two galaxy clusters that are both filled with this hot gas, and they just slam into each other. The hot gas, when it slams into itself and stops and shocks a little bit. So it's kind of like if you had two buckets of water and you threw buckets of water at each other. The buckets of water would slam, the water would all hit itself and kind of stop in the middle. Okay, so that's kind of what's happened. These things have kind of slopped and stood still. But this blue stuff, the stuff that makes up this is actually dark matter, I think. Dark matter has kept going. It hasn't stopped because it doesn't interact. It just goes right through. So the normal mass has interacted, has run into itself. But the blue stuff, which we think is coming from the dark matter, has not. So we think what's happened is the gas ran into itself and the dark matter did not. And so we really are seeing direct evidence that the dark matter doesn't behave like normal stuff. It behaves differently in this weird way. That stuff that doesn't interact behaves. Is there a question about this?
So are they both moving towards each other so that the dark matter will run into
Yeah, so now what's going to happen, we think what's going to happen is they've come through each other and now they're going to slosh back and get all mixed up. So in a little while you won't be able to see any of this and it'll all be mixed up again. So what we think is really happening is a bigger cluster is about to form. So this is how we think big galaxy clusters form. They eat up little smaller galaxy clusters. Any other questions? So what is this dark matter? Like I said, we don't know. We don't know, but we have ideas, I guess is the best way to say it. Dark because it doesn't shine, and matter because it's attracted to other matter by gravity. That's the main thing that it does. It tugs on other stuff with gravity. Okay. And we don't know what it is, but most cosmologists, like I said, think it's some form of subatomic particle that has not been discovered. The other thing that's going on is people are looking for it. Okay? So what we think is going on is we live in a galaxy like the Milky Way, and the sun is sitting here. And we think that the whole galaxy is surrounded by this huge diffuse cloud of dark matter. And the dark matter is made up of lots and lots and lots of little particles that are zooming around. And since the Earth is here, a bunch of those particles are coming through the Earth all the time. And leading theories, although this is just a theory, suggest that there's something like 600 million dark matter particles passing through all the time.
So
yeah.
So it's here with us
Now,
now?
it's going through the room.
Oh, okay.
It's just coming through, but we can't feel it. Right? Now you might think this is stupid. This is just crazy. Okay, but I can tell you that there are particles going through us all the time that you can't feel. One type of particle that's going through us all the time is photons from radio waves. And I know that because my phone has a signal. Right? It has a signal when it's in my pocket, or whether I turn this way or this way. There's photons going through me all the time. So there's stuff going through you all the time that you can't detect. But we've built instruments that detect the radio waves. There's other type of particles that we know about that are going through us all the time that are much harder to detect. Those are called neutrinos. There's a certain type of particle called neutrino that was only discovered fairly recently. In fact, Fred Reines got a Nobel Prize for it, and that's the name of the building right across the hall, or right across the way here. So he was a professor at UCI. He discovered neutrino, got a Nobel Prize. It's a really hard thing to discover because they're very, very weakly interacting. We think neutrinos are going through us all the time. In fact, we know they are. And those have been detected. So there are particles, there are things that go through us that we cannot detect, that don't do anything to us all the time. Yeah? What are neutrinos? So neutrinos are a type of particle that are released in things called weak interactions. So there are things called weak interactions associated with radioactive decay that create neutrinos. And one way to think about it is, there's a certain reaction where you can take a proton and combine it with an electron, and it can emerge as a neutron and a neutrino. You can take a proton and an electron, they can go together, and out comes a neutron and a neutrino. So those kind of interactions happen. So interactions like that between elementary particles. And you know, it's subtle. It's not the kind of thing that happens every day, but it's the kind of thing that was determined when people started trying to figure out how radioactivity works. And so people, like nuclear physicists, people who want to study how to make nuclear reactors, things like that, understand neutrinos. We see them all the time. They're generated in the sun all the time. They're streaming at us from the sun all the time. And scientists today study them pretty regularly. We didn't know about them 100 years ago. Okay? So this idea that there are particles that exist that are not easily detected is not necessarily crazy. But let me tell you why this matters, well, why you might think this is interesting. You know, 40% of you are asleep, but there's about 20% of you who are really interested in this. That's why I'm going to keep talking. Yeah?
How can we estimate the number of dark particles if they don't know?
If we don't know anything about them, that's good. So there are theories that exist. So there are sort of less empirically solid theories that exist that think they know how massive each of the dark matter particles is. Okay? And from that, you can determine how many we think are coming through us all the time. So there's a... so we think we have a fairly good unified sort of standard model of particle physics that more or less explains everything in the periodic table plus everything else we've ever observed, except for the dark matter, more or less. Okay, and that theory, while it works really well, is very ugly. It's a very ugly equation that, you know, if I wrote really small, you could write it over all the chalkboards. It's like one big, long, ugly equation. And so, and there are certain things about it that are ugly in an aesthetic sense. And so there are theories that are proposed that will make it, that suggest that there's some simpler, more beautiful theory that sits up here that describes it. And in those theories that people develop to try to create, you know, this sort of beautiful universe, there are all these particles that have to exist that we haven't seen yet. And the existence of those, and that's one of the reasons why people like those theories, because they actually predict the existence of dark matter. So if we see it, it can inform those theories. I kind of stumbled through that. I wasn't ready for the question. So anyway, people are looking for this. Maybe I just want to get down to it. So the idea is we think that it should be possible to detect this, to detect these dark matter particles coming through. What we think they can do is, if you set up a detector that's very, very, very sensitive, in principle you can detect the dark matter coming in, interacting with atomic nuclei, making them wiggle. You can detect that wiggle. And in detecting that wiggle, you're detecting this wind of dark matter that should be passing through the Earth. The second way that people are looking for the dark matter is actually using gamma ray telescopes. So we think that in most of these models, that if you pack dark matter tightly enough together, it can eventually start to interact, and in that interaction produce gamma rays. And so we think that the center of the galaxy, in principle, should be shining in gamma rays from this. And the centers of all the little dwarf galaxies ought to be shining in gamma rays. And there's an ongoing effort to use gamma ray telescopes to do this. Finally, there's a hope that within the next few years that we can actually create dark matter. There's something called the Large Hadron Collider that's being built in Switzerland, which is the world's most powerful particle accelerator. And so the idea is they speed up these particles really fast, going around a ring using magnets. And the ring is 17 miles. And then they spin up another one going the other way around. So I can't do this, but one goes this way and one goes that way. And then they let them slam head on into each other. And in that collision, they create such a powerful collision with such high temperatures. There are temperatures that have never been reached, as far as we know, except for right after the Big Bang. So you're recreating conditions in the very early universe, and in doing this, it's possible that we could actually create the dark matter itself in the laboratory. If we did this, again, this would be exciting and be another, then that would be solid evidence that this stuff actually does exist. And what's interesting about this is a, yeah.
How did you know that you created it if you can't see it and it doesn't have
What?
to interact?
Right. So what you detect, the question is, how do you know you detected it if you can't see it or it doesn't interact with anything? Great question. So it reminds me of a story I'll tell when I finish this. So what you look for is you look for something missing. Okay. So we think that, for example, energy is conserved. So we can measure all the energies of the energy of all the particles coming in, and we can measure the energy of all the particles coming out. If we count up all the energy coming in and we count up all the energy coming out, and it's not the same, there's something missing. So it's that missing stuff that we can't account for is like, aha, that's evidence that something's there. And you can figure out how much mass it had, too. And if it has the mass that I was talking about, that this idea that whatever the mass is, it's all self-consistent within this picture, then that's what's happening. So that reminds me, let me say one thing and then we'll be done. So I was giving a lecture kind of like this. I know you guys may find this hard to believe, but there are some people who actually come of their own volition without having to take a class to listen to stuff like this. So I was giving this public lecture one time in Aspen. And I was giving a lecture and I was talking about dark matter going through walls. And I said, well, let's say you had a tennis ball gun. You shot a tennis ball gun at the wall, the tennis ball would bounce off the wall. If I had a dark matter gun, and I shot the dark matter gun at the wall, the dark matter would go right through the wall. A little kid in the front row, who's like 8 years old, raises his hand and says, well, if you can't interact with anything, how do you shoot it with a gun? And I was, he was totally right. And I said, you want to come to UC Irvine and go to school? But yeah, he's right. So I never use the gun anymore. So now if you remember what I said in this lecture, I just said, if you had a ball of dark matter and it was moving through the wall. Because I don't know how to get a ball of dark matter to go to the wall. All right, that's it. See you guys on Thursday.